Okay, so as you can see, today we're going to talk about quantum mechanics and also about particle physics. I don't have my slide clicker, I'm afraid, so I can't point to anything, but the slides will progress nonetheless. So quantum mechanics. What can we say about quantum mechanics? Well, prior to the 1900s, physics is seen in a very deterministic way. So if you know enough about the laws of nature, you know enough about the initial setup of your system, and you can calculate things well enough, you can work out how your system is going to look, how it's going to behave at some later time in the future. Quantum mechanics completely does away with this notion that you can know exactly how something is going to look at a certain time in the future. It instead replaces this deterministic picture of the laws of nature with a probabilistic picture. So rather than asking questions like, where is this tennis ball? If I kick it with a certain speed, in a certain direction, where is it 10 seconds later? Quantum mechanics doesn't answer the tennis ball is over here at this time with this speed. Quantum mechanics answers there's a 50% chance it's in this area of space over here when you look at it, there's a 30% chance it's over here, and there's a 20% chance it's, I think I've done my maths wrong there, there's a some percentage chance that it's anywhere completely else in the universe, okay? So it's a completely different way of thinking about the laws of nature, but nonetheless it is science. That is perhaps the most bizarre thing about quantum mechanics. As we go through, we'll look at lots of bizarre properties it has, but the weirdest thing is that it's something we can test, it's true, and it is science. Many aspects of our modern world are built upon the principles of quantum mechanics. These bizarre ideas, we'll look at Schrodinger's cat as an example of some of these bizarre ideas. But if ever you have an MRI, you are using in the design of that machinery the principles of quantum mechanics. If you use a GPS, the GPS systems, if you got here via GPS technology, rely on super accurate atomic clocks, which again work on the principles of quantum mechanics. So this stuff might sound fanciful and bizarre, but it's real science, and when we apply it to engineering problems, we can make incredible things using this. Okay, next slide, please. I have to stand even closer. It's not that good. Okay. So an outline of what we're going to talk about. First of all, we're going to talk about the death of classical physics, with a bit of an asterisk there because we still use classical physics for a lot of things, so it's not completely dead. We're going to talk about the birth of quantum mechanics and how we interpret the sort of bizarre rules and laws that quantum mechanics seems to suggest. And then we're going to take that a step further and look at an even more advanced theory that is called quantum field theory, which is the sort of love child of quantum mechanics and Einstein's theory of special relativity, and is even more bizarre in many ways than quantum mechanics. Then, hopefully we'll have time, because we lost a little bit, we'll come on to talk about the particle zoo, which is this host of particles that were discovered in the early 1950s through to the 1960s that couldn't be explained in a sort of simple and straightforward way. It just looked like physics was turning into botany or stamp collecting. We just found millions, well, not millions, we found hundreds of these subatomic particles that we couldn't understand in one framework. But we managed to solve that, fortunately, which will bring us on to the standard model of particle physics, which is our most up-to-date, most accurate theory of what matter is made of in the universe and what are the fundamental forces that govern their interactions. I say it's the most up-to-date and most accurate. It only accounts for about 5% of the stuff in the universe, and it misses one of the most important forces in the universe as well, which is gravity. So we have some work to do. Then we're going to talk about dark matter, and possibly after that talk about potential future theories that might replace or augment the standard model to include dark matter, and perhaps even to include gravity. Okay? Next slide, please.
Sorry, what was the picture of?
Oh, yeah, do you want to go back again? So this is part of the Large Hadron Collider. I think this is the detector in the ALICE experiment, as far as I know. So, these panels here are designed to detect subatomic particles formed when we crash protons together at very, very high energies. So we'll talk a little bit about particle accelerators later, but this is how we sort of understand what different particles there are in the universe. Yeah?
What's the diameter of that?
Oh, I don't know. I think it's a few stories. It's enormous, actually. I think it might even be... I can't remember exactly where this picture's from, but there's part of the ALICE detector which is about 2 stories tall. It's pretty big. Okay. Next slide, please. Okay, so classical physics. This is the sort of recipe for how physics was done prior to the early 20th century. We have some initial state. You have laws of physics. You apply your laws of physics with sufficient knowledge of the laws of nature, sufficient computational power, whether that's doing it pen and paper, biological computation, or mechanical computation using computers, which is more often what we have to do now. And you end up with some final state. So next slide, please. So as an example, suppose I kick a golf ball upwards with a certain speed, 10 meters per second. That's my initial state, my initial position. I apply some of Newton's laws of motion, which will be familiar to any of you that do A-level physics. And then in the end, I come out with the location of the golf ball, which is 0.38 meters above the ground. Okay? So this is a typical calculation in classical physics. Next slide, please. Okay. So classical physics is broadly divided into 4 rough areas. There's classical mechanics, which is Newton's laws, how things move, mechanical systems, thermodynamics, which is about heat, how heat flows, building engines, all stuff to do with things that are hot and things that move heat around. Electromagnetism, which is about electricity, electrical circuits, magnets, and how these 2 things are actually related. And optics, which is all about light, how light works, at least in a classical way. Okay? What else did I say here? Yeah, so classical physics is still extremely useful. We don't do any quantum mechanics when we're building rockets to take us into space. That's all still classical. So it's not that classical physics is completely dead and completely useless, despite the heading I used on the outline. But it has in many ways been supplanted by quantum mechanics as a fundamental theory of what's going on in the universe. Okay? Next slide, please. Yes, so quantum mechanics disabuses us of this notion that with sufficient information, sufficient knowledge, and sufficient computational power, we can work out the final state of a system. Okay? Next slide, please. So, how did we first figure out that this was not quite how the universe works? Well, it goes back to 1900, well, a little bit before 1900, actually. Physicists had worked out that if something has a temperature above 0, and when I say 0, I mean absolute 0. So there's a minimum temperature below which you can't cool things down anymore. Because once you've cooled them down to this temperature, we call absolute 0. They've lost all of their kinetic motion, the particles that make up the substance. And once they've got 0 kinetic motion, you can't take away anymore. So we call this absolute 0. In Celsius, it's about minus 273. So it's very cold. But nothing is colder than that. So anything that has a temperature above absolute 0, so above minus 273 Celsius, will emit thermal radiation. This is why, for example, hot coals appear to glow orange. Because they're very hot, the thermal radiation they emit is in the visible part of the spectrum, and we can see it. It's also why colder objects like living organisms, like mammals, will emit radiation of a slightly longer wavelength in the infrared part of the spectrum. This is how night vision goggles work. Thermal radiation, actually, can we go to the next slide? There we go. So thermal radiation is just electromagnetic radiation. So it's the same phenomena as visible light. Okay? So the electromagnetic spectrum is divided into these separate parts here. So, gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. But it's a continuous spectrum. It's all one single phenomena, an electromagnetic wave that's formed of alternating, oscillating electric fields and magnetic fields, replicating themselves through space. And this is what thermal radiation is. Despite these different names for the different parts of the spectrum, visible, gamma, and so on, it's all one phenomena, an electromagnetic wave. Okay. Next slide, please. Problem is not having a laptop. I can't remember what the next slide is. Okay, so the color something appears to glow when it's very hot is related to how hot it is. So, you've all heard the expression red hot to mean something very hot. Well, actually, red is about as cold as something can be if it glows hot enough for us to see. Blue hot is much hotter than red hot. So, for example, Rigel, which is a blue supergiant, has a temperature of about 12,000 Kelvin, whereas Betelgeuse, which is a red supergiant, has a much lower temperature of about 3,800 Kelvin. So Rigel is hotter, so it glows bluer rather than redder. And some things are so hot that the peak of the frequencies of light they emit is actually outside of the visible region. So a lot of things are so hot that they're emitting even higher energy light rays, like ultraviolet light. And some things are so much colder that they're not emitting really any visible light, and they instead emit in the infrared. So we could see them with a night vision camera. Okay. Next slide. Okay, yeah. So this graph, I want you to focus on the curve on the sort of upper left part that says 8,000 K, 8,000 Kelvin. And then I want you to focus on this dotted line here that says classical theory. So in 1900, physicists who had observed experimentally that hot objects release this thermal radiation, they glow when they get hot, they had figured out experimentally just exactly what proportion of the thermal radiation emitted fits into what part of the electromagnetic spectrum. So here you can see the sort of colors of the rainbow are superimposed. What this is showing is that something that is colder, like this 4,000 Kelvin, so that's basically 4,000 Celsius object, is peaking more in the red region, whereas the 6,000 Kelvin curve, the one just above it, is peaking more in the blue region. So this is showing that hotter things, again, emit more blue light than red light. So the solid curves are what we observe in nature and can model in a laboratory. Well, you can't get temperatures that high in a laboratory, but we produced similar curves for lower temperatures. But if you apply the classical theory of thermodynamics that existed at this time, so 1900, you get a curve that completely misses what's really going on. So we have the solid 8,000 curve, and we have the dotted 8,000 curve that is the theoretical prediction. So there's a clear disparity there. Our theory, our calculations, are not remotely matching what is seen experimentally, what we observe. And this was called the ultraviolet catastrophe. Quite a sort of dramatic name for a physicist. But the reason we call it this is that in this sort of ultraviolet region, and actually a lot outside the ultraviolet too, the theoretical calculation is completely diverging from the real experimental idea of what's going on. Okay? Next slide, please. Okay, so there's a great quote here by Richard Feynman, which I won't go through entirely, but the idea here is that if something disagrees with experiment, it's wrong. So we have here a disagreement with experiment. We have our classical theory, the equations from classical physics, and we have the observations of what's really going on, and there's a huge difference. Okay? So next slide, please. That's all well and good. If it disagrees with experiment, it's wrong. However, wrongness is a spectrum. some things are more wrong than others. And what does it mean to be wrong in the first place? So, in physics, we don't really talk about absolute truth. This is quite a delicate notion, and we're a bit heavy-handed, so we don't tend to touch it. Instead, science deals with models. So, a model is a description of a physical system that allows us to understand some aspects of that physical system. We don't claim that our equations come directly from God and they describe exactly what's going on, but they make some predictions that are testable, that we can compare with experiment. The model doesn't even have to work in all circumstances. As long as it describes some aspects of the system within some range of parameters, then it's a good model. Okay? So for example, Newton versus Einstein, they're two theories of gravity. Next slide, please. Right, so Newton versus Einstein is a good example. Newton's theory of gravity is what allows us to understand mostly what's going on with the planets in our solar system. It's what we use to calculate trajectories and orbits when we fire rockets into space, but it's not the full picture. So Einstein, a couple of hundred years after Newton, well, about 150, 160 years after Newton, introduces his theory of gravity, which is completely different to Newton's. It replaces almost every idea that Newton has about gravity. And it predicts new things. It predicts things like black holes. It describes certain subtleties with Mercury's orbit that Newton's theory had struggled to describe for decades and decades. So it extends Newton's theory. Next slide, please. So Newton's theory works in its sort of ballpark. It works for relatively small masses, not very super high densities like you would find in a black hole. But Einstein's theory picks up where Newton's left off, and it tells us more about heavier objects and denser objects. Okay, next slide, please. So, so what I wanted to say just before that is, it's not then that Newton's theory is wrong, but it's that it's not the full picture. It's like if you're looking at cells in biology through a microscope. What we're doing when we go from Newton's theory of gravity to Einstein's theory of gravity is we're just zooming in at a higher magnitude. We're going from 10 times zoom to 100 times zoom. It's not that the 10 times zoom picture is not really what the things look like, but it's that we're looking at a higher level of detail when we upgrade the zoom on our microscope. So we pick up details we weren't previously aware of. Okay? And even Einstein's theory of gravity is not the final theory of gravity. There are lots of problems with Einstein's theory. Eventually, we expect this will be replaced with a quantum theory of gravity. But again, that won't mean that Einstein is completely wrong. Einstein's stuff is perfectly good for very heavy masses, but it can't go down to super high densities like the center of a black hole. If we want to understand those things, we have to go further. Okay? Next slide, please. So when there is insufficient theory to explain the observations of our experiments, new theory is needed. Next slide, please. Okay. So theory in physics and in science has a much stronger meaning than it has in our everyday language. If you say you have a theory about something, it kind of just means you might have a gut feeling, or you might have a guess, or it can mean something quite sort of fluffy. Okay, but a theory in physics is a lot less fluffy. It's a lot more concrete, and it builds on what has been done before. So a theory in physics must have some kind of evidence, even if it's not proven. It has to come from somewhere. So it will either come from an experimental proof. This is the kind of gold standard. If you can prove your theory works with an experiment, this is very good. That's a good theory. But there is also theoretical evidence, which is a little bit more controversial and sounds a bit post-truth. But the idea here is that in theoretical physics, often it's not possible for us to test our ideas in an experiment perhaps for a very long time, perhaps decades after we've died, as is now really seeming like the case. But it forms part of it emerges from a framework of ideas we've come up with before and have tested. It relies on our use of mathematics, which is crucial in physics. So there is somewhere it comes from. It's not just a guess. When we're talking about some of these ideas later on, they might sound fanciful and it might sound, oh, well, what if the universe is made of these undulating, oscillating quantum fields? Wouldn't that be cool? Let's see what that means. But these ideas haven't just sprung out like that from nowhere. They don't come from thinking sort of in terms of words. They come from thinking mathematically. They come from a deep and challenging and complex theoretical background. Okay? That's me getting away with not having to justify everything I'm going to say. Okay? Next slide, please. Did it change? I can't remember.
There was a however at the bottom.
Oh, it did change. Oh, okay. However, what was it? I've forgotten. Yeah, so however, given that I've said a theory in science is not just a guess, quantum mechanics and the origins of quantum mechanics really tests that not a guess rule to breaking point. Okay? But what I want you to keep in mind is that despite the sort of quite flaky origins of quantum mechanics, it has since been tested more than any other theory we have in nature. The predictions of quantum mechanics in a specific region, in a specific application, which is about how electrons interact with one another, in some cases has been tested to 1 part in a trillion and is correct. So, that's like you make a prediction for what the number should be, and it's correct to what the theory says to the 12th decimal place, 1 part in a trillion. So it's been tested extremely rigorously. Okay? Next slide, please. Okay, so we've spoken about the ultraviolet catastrophe and the problems this causes for classical physics at the time, this massive discrepancy between the theoretical prediction and the observed spectrum of radiation coming from hot objects. So in 1900, Max Planck posits a mathematical solution to what's going on. So he modifies the equations of classical physics very slightly by making an assumption. He assumes that the energy carried by the thermal radiation, carried by these electromagnetic waves emanating from a hot object, are quantized, meaning they are discrete packets of energy. If you're delivering energy continuously, it's like turning on a tap, right? You can turn on the tap for as short a time as you like, and you can deliver the tiniest amount of energy, or if you leave it on, you deliver more energy. Having the energy quantized is like you've got little water balloons full of water. I can throw a whole water balloon at you, or I can not throw a water balloon at you, but I can't throw half a water balloon at you, okay? So he's applying a mathematical trick to turn the energy of the light rays coming from a hot object into discrete packets of energy. Okay, next slide, please. And wow, that's my feeling of this, because it seems completely out of the blue, completely random. Why would he think to do that? But he did, nonetheless, basically through mathematical insight. But Einstein comes along a few years later, and he interprets this mathematical trick that Planck has performed as light being composed not of waves, which was the prevailing opinion for some couple hundred years before that, but instead being composed as a sort of machine gun fire of these little particles of light we call photons. Okay? And he uses this theory, this idea that light is made of photons, to solve another problem in physics, which is the understanding of something called the photoelectric effect. So he uses this, and he wins the Nobel Prize a couple of years later. Next slide, please. Okay. So Einstein is telling us light is made of particles, photons. Why am I still using the term electromagnetic wave, as I have been throughout this talk? Next slide, please. It turns out it's both. Next slide, please. But also neither, as we will discuss. Next slide, please. So, what do we have? We have some evidence that light is acting as a wave. So this is this top experiment here, where if you pass a ray of light through a pair of slits, a pair of gaps in an opaque screen, the light waves will spread out as they pass through each gap, and they will interfere, meaning wherever a peak, the top of the wave, you can think of water waves in the same way, passes over the peak of another wave, the wave gets bigger. But if the peak passes under a trough, the bottom of the water wave, or the light wave in this case, they cancel out. So we see bright patches and we see dark patches, where sometimes they're cancelling, where one is up, one is down, and sometimes they're reinforcing. And this is a fundamentally wave phenomena. This is something you only see with waves. But as I mentioned, Einstein, when he's doing his work on the photoelectric effect, shows that you can only explain what's going on here, and I won't go into the details of what's going on here, but basically, if you fire light at a piece of metal held in a vacuum, sparks jump off of it. But there's something specific about the energies of these sparks that tells you something a bit more deep. But he proves you can only explain what's going on here if light is behaving as particles. So we have contrary evidence. So this is not a sort of typical moment in physics where you have an experiment that you can't understand, and then you come up with a theory, and you find you can understand it with your new theory. This is, we have two experiments and two theories, and they both only work if the contrary cases are true. So it's a complete contradiction, okay? Next slide, please. So there's clearly something strange going on here, something not usual. Next slide, please. So it gets worse. Not only does light have this strange property, where sometimes we can talk about it as a wave, and sometimes we can talk about it as a particle, a photon of light, but all matter particles exhibit this strange indecision, this wave-particle duality, as we call it. So to explain this, I want to describe an effect to you we call diffraction. So this, again, is a wave-like property. So you can see it here with water waves passing between two rocks. When water waves pass through a gap that is similar to the spacing between the peaks of the waves, the wavelength, they will spread out. So that you can see here these water waves are kind of fanning out after the wave passes between the gaps. Okay? And all matter exhibits this wave-like property. Next slide, please. Okay, so given that I am made out of matter, and the wave-particle duality is therefore saying I should exhibit some kind of wave-like properties, why do I not undergo this process of diffraction? For example, when I pass through a doorway. Okay, next slide, please. So the key is in this line here, where diffraction only occurs if the wavelength, so the spacing between two peaks of the wave, is similar to the gap they pass through. Okay? So what is my wavelength? How does my wavelength compare to the size of a doorway? Next slide, please. Okay, so the formula we use to calculate the wavelength of a matter particle comes to us from Louis de Broglie, who has the title of the most mispronounced name in all of physics. I think even I'm pronouncing it now. The worst version is de Broglie. It's not de Broglie. The slightly better version is de Broglie, which is what I go for. But I think the true version is something difficult and French-sounding that I'm not going to attempt. So we can calculate the effective wavelength of a piece of matter. It depends on two things. It depends on the mass of the piece of matter, and it depends on how fast the piece of matter is moving. So I've taken average walking speed of 1.2 meters per second. I've taken my mass as 135 kilos, because I'm a big chap. And I'm calculating the wavelength of myself as a matter particle moving at that speed. And what you see is that when I do this calculation, I get an extremely tiny number. So remember from last week, this 10 to the minus 36 means 36 jumps backwards before you get to the decimal point. So 0 point, and then there's about 35 zeros after that, and then a 4. Now, obviously, this is extremely different in size to the size of the doorway, so I'm not going to diffract. I won't demonstrate it, because you know what's not going to happen. I won't diffract when I pass through the doorway. So the length scale at which quantum behavior will be apparent for me, as myself as a piece of matter, is so much smaller than my dimensions, and smaller even than the size of the nucleus, by a factor of about 10 to the 15, smaller than the nucleus. So that's why I don't see any quantum behavior at our length scale. Okay? Next slide, please. Yeah, so we don't see any behavior quantum mechanically at our own length scale. However, it does affect things at the subatomic scale. That's the point. So, the laws of quantum mechanics. Believe it or not, as lawless as it sounds, there are some concrete laws to quantum mechanics. The main law that governs how quantum mechanics works is this equation here, Schrodinger's equation. So 1926, Erwin Schrodinger, between juggling his several mistresses that got him kicked out of Oxford, discovers this equation that when solved, if you go to the next slide, please, tells us this thing we call the wave function. The other thing I just wanted to point out, which is always remarkable about this equation, is that you can't write down this equation without using an imaginary number. Okay? If you've never heard of an imaginary number, this is the solution to the square root of -1, which you might think, well, how can you have the square root of a negative number? Because when you take a square root, that's asking the question, what two identical numbers multiply to give the thing inside the square root? So for example, 25, the square root, you have 5 times 5, or -5 times -5. The square root of a negative number surely makes no sense, because any two identical numbers will multiply to make a positive thing. Because a positive times a positive makes positive, but also a negative times a negative makes a positive. So this shouldn't exist, but it does. It just adds to the numbers we have that you can count, decimals and so on, the real numbers. It adds to it by adding a new imaginary direction to the number line. The point is, this is physics. This is real predictions of what stuff is going to look like, but it involves an imaginary number, and I always find that kind of neat. But anyway, so this thing I've called the wave function here. This is a mathematical variable, which in many ways behaves exactly like a wave. So it looks, if you plot it, like a wave. But what it actually represents is a probability. Okay? It becomes a probability distribution. So Schrodinger's equation, by the way, is a difficult equation to solve. It's not one that can be done in a lot of contexts, pen and paper. A lot of the time you have to use a computer to do it. But the thing you get from solving Schrodinger's equation is this thing called the wave function. Next slide, please. Okay, we'll come back to the wave function in a moment. So the laws of quantum mechanics, distinct to the laws of classical physics, of classical mechanics. Recall previously, we had an initial state. We have the laws of physics. We apply the laws of physics to our initial state, and then we come up with some final state. This is fully deterministic, because if you know what's going on, you know how to do the calculations, you figure out what happens at the end, you get your final state. Quantum mechanics gets rid of this deterministic view of reality and replaces it with a probabilistic view. So now I start with some initial state. I apply the laws of quantum mechanics, so Schrodinger's equation we just saw, and instead of an exact description of what the final state is, I end up with a range of probabilities. For example, for finding the system in a particular final state. Okay? Next slide, please. So for example, remember before we looked at a golf ball. If I hit the golf ball upwards, I apply the laws of classical mechanics, and I find out where the golf ball is sometime later. Now I, for example, fire an electron at a gap, at a slit or something. I apply the laws of quantum mechanics, meaning solving Schrodinger's equation. I find this little blue symbol here that's called psi, the wave function. And the wave function then turns into a probability distribution. Specifically, you have to square the wave function to turn it into a probability, but we don't have to worry about that. So instead of telling me exactly where the electron is on the other side of the slit, it gives me a distribution where the higher the distribution, the peak in the middle, tells me I'm most likely to find the electron there. But then there are these other peaks, these other regions where the distribution is not zero, where it's telling me I might also find the electron here. It's less likely, but it's not impossible. The point is I can't tell you where the electron is at this stage. All I have is a probability distribution that tells me where is it more likely to be found after passing through the slit. Okay? Next slide, please. So, but surely the electron must really be somewhere. Surely I just don't know enough, right? Next slide, please. Yes and no. Next slide again, please. So there is a fourth step. So we've done our calculation. We've come up with our probabilities. The fourth step is now to make an observation. So to actually take a look at where the electron is. Okay? So this fourth step here, where I look and see, well, where actually is the electron, we call the wave function collapse. So after this point where I make the measurement, the position of the electron is now known. It's a definitive position. Okay? But the point is, until I make that observation, until I look at where the electron is, it really does not have a definitive position. It isn't just that I don't know it, it's that it really does not have one. Okay? Next slide, please. So the way I can sort of describe this, what I want you to remember about quantum mechanics for now, is that matter behaves as a sort of fuzzy cloud of probability until you make an observation, and then it does not behave like that anymore. Then matter takes a definitive location in space. Okay? So these are the four steps. Initial state, the quantum mechanical fuzzy cloud, probability distribution, telling you where it's more likely to be found, and then after an observation, we know where it is. Okay? Next slide, please. So, seems simple, right? Next slide, please. Not remotely simple. These are two Nobel Prize winners. So Richard Feynman saying, if you think you understand quantum mechanics, you don't understand quantum mechanics. And Roger Penrose, quantum mechanics makes absolutely no sense, which again is very true. Okay? But I want to make another point, though. It's true that it doesn't make sense intuitively to us. But we have equations, we can make predictions, we can build technology on the principles of quantum mechanics. So although it sounds crazy, it's not sort of mystical astrology level craziness. It's real stuff, it's real science. Okay? Next slide, please. Okay, what is this one? Right. Interpretations of quantum mechanics. So there are three interpretations I've written here. So we're going to talk through three of them, and then I want you to tell me which one you prefer at the end. So we have, first of all, the Copenhagen interpretation. This one says it really is just probabilistic. The laws of nature at the most fundamental level are about probabilities. We don't know what's going on until you make a measurement, then it stops being probabilistic, and you know where something is. Okay? So shut up and calculate, basically. The many worlds interpretation, which says, as I mentioned briefly earlier on, every time the universe has an opportunity to make a choice between something happening or something not happening, the universe splits into two parallel universes, one universe in which the thing was always going to happen, and one universe in which the thing was never going to happen. Okay? But the point is, you don't know which universe you're in until it happens. So again, you can't use this to say, oh, well, that was definitely going to happen. That was never going to happen, because you don't know until it does happen. Okay? And thirdly, hidden variables. So this interpretation says, surely this is not the way the universe works. Surely nature is not indeterminate at a fundamental level. Things must be deterministic. We just don't know enough about the laws of nature. It should be classical. Okay? So I want you to stick your hand up if you prefer the Copenhagen interpretation. And be honest. Oh, okay, all right. Stick your hand up if you prefer the many worlds interpretation. Okay, not many. Stick your hands up if you prefer the hidden variables interpretation. Aha, okay. So the allure of hidden variables is very real. Next slide, please. Hidden variables is the only one of these we know is not true. The reason it's not true is a little bit tricky, and I'm not going to try to get into it right now, but it comes from, again, real pieces of science, real concrete predictions you can make based on the assumption that there are these hidden variables of which we are not aware, which are contradicted by an experiment. It's a bit complicated to explain this part, but it won the Nobel Prize only a few years ago, actually. This is the only one that is not true, okay? And you just have to take my word for it for now. There are some ways of getting around it. You can have non-local hidden variables. That gets even crazier. But hidden variables is ruled out. The two that are not ruled out, and are actually both equally plausible, equally sensible, and equally crazy at the same time, are the Copenhagen and the many worlds interpretation. And we can't distinguish between them. There's no way of distinguishing between the different interpretations of quantum mechanics that we know of yet. We might figure out something in the future, but there aren't really any ideas of how to distinguish these two at the moment. Okay, next slide, please. So the many worlds interpretation, this is sometimes called the multiverse, which I think has not yet been trademarked, so I can still probably say it. There are different levels of multiverse we sometimes talk about in physics. I mean, I say in physics. Physics is the study of the universe. This is going a bit beyond that. So this is not, in a way, something scientific. We can't, again, distinguish between whether the many worlds interpretation is true or whether the Copenhagen interpretation is true. But nonetheless, physicists have categorized some of the different kinds of multiverse that might exist. So the one we've actually been talking about is this bottom one, which is a sort of Everett multiverse, a level 3 multiverse, which comes from the many worlds interpretation of quantum mechanics. So this, again, is the idea that when there's a choice between two outcomes, so here, boy is giving a girl a flower, two outcomes, girl falls in love with boy, girl does not fall in love with boy. Whenever there is an option, the universe fissions. So we are on one of these strands in which these outcomes were always going to happen in a deterministic way. But we have no way of knowing which strand we're on. So you still can't predict what's going to happen in any meaningful way. It still appears to be probabilistic, but there's some higher space in which we live where this path was always going to happen. Okay? The other kind of multiverse is a little bit less, well, it's something we might actually be able at some point to make predictions about. You might remember last week we spoke about inflation, this very rapid expansion of the universe. Well, what happens in this process of inflation is certain parts of the universe become entirely causally disconnected from one another. And it's possible that these different parts of the universe might have slightly different laws of physics, meaning there might be patches of, this sort of grander space which contains our visible universe, our observable universe, in which there are little pockets that have different laws of physics, different kinds of matter. We'd have really no way of knowing. Again, we can't detect or we can't make predictions about this, so it's a little bit of a stretch to even call it physics. But I thought I'd include it because people like to hear about the multiverse. Okay? Next slide, please. Okay, so Schrodinger's cat. What is Schrodinger's cat? Well, really, this is an analogy, or it's a thought experiment to try and explain two of the interpretations of quantum mechanics, Copenhagen and many worlds. So the idea is you place a cat in a box, you have a vial of poison in a glass vial, and you have some radioactive source which, if an atom in this source decays, it will trigger the hammer to smash the poison and kill the cat, sadly. If the atom does not decay, the hammer will stay where it is and the poison will not be smashed and the cat will live. But this radioactive decay of the atoms in this radioactive source is a completely random process. Okay? It's all about probability. It either happens or it doesn't with equal probability. You can't tell when it's going to decay. You can't tell if it's going to decay. You can't make a prediction on that. Okay? Next slide, please. So in the many worlds interpretation, when the cat is placed into this box, there are two possible outcomes. Either the vial smashes and the cat dies, or the vial is not smashed and the cat does not die. Now, at the point where this decision for the universe to make is put in front of it, the universe splits into two. There is a universe in which the poison was never going to smash and the cat would always be alive. And even though I've not yet opened the box, the cat is in that state. It is alive. I just don't know it, okay? Because I don't know I'm in the universe where the cat was always going to live. The other case is where the hammer does smash the glass vial, the poison is released, and the cat does die. So these two branches here are two different universes, okay? Again, I have no idea of knowing which universe I'm in, but before I even open the box, the cat is dead when it's inside, okay? And of course, when I open it, there's a living cat in there. There's a 100% chance I will see a living cat when I open it up. And in the top branch, the cat is dead inside, and there's a 100% chance when I open the box, I will find a dead cat, okay? So that's the many worlds interpretation. It splits at the moment the decision is put in front of it, and then you're in one of these branches, but you have no way of knowing which one until you open the box, okay? Next slide. The Copenhagen interpretation, on the other hand, says that before I open the box, the cat is in some indeterminate state where it is both dead and alive, neither dead and alive, however you want to put it. And it's only at the point where I make an observation of the cat inside the box that the universe chooses the cat is living or the cat is dead. But until I open up the box and make the observation, the cat is in this sort of fuzzy, indeterminate state we mentioned before, where it's described really, when it's in this indeterminate state, by a probability distribution. 50% chance dead, 50% chance alive. But it doesn't make up its mind about which one it is until the observation is made. Okay? Next slide, please. Okay, so we've got half an hour left, so we should be able to get through most of what I want to talk about. I want to talk a little bit now about particle physics. Actually, before we talk about particle physics, so we're kind of coming on to the end of the quantum-y stuff for now. Does anyone have any quantum-related questions? Or perhaps just stunned silence? Yep.
When you put the cat in the box, you knew it was alive.
That's right.
So you don't need to open it because you knew it was alive.
But the point is, you go back a bit, actually. The point is that it's connected up to this radioactive source that has a 50% chance of smashing the poison to kill it, or a 50% chance of not smashing the poison to kill it. So although when it goes in, I know it's alive, once I close the box and the system starts running, it's either going to be killed or not killed by the poison.
So that could still have happened. That could have happened.
What could have happened?
That the radioactive.
Oh yeah. So here.
Been activated.
Yeah, exactly. So here it's like a 50% chance it will or it won't. So in the Copenhagen interpretation, 50% chance before I open the box, the cat exists in this quantum superposition where it is neither dead nor alive. It's a mix of the two. It's both at the same time, which is a hard thing to get your head around. But these superpositions are everywhere in quantum mechanics. You know, in the same way when I showed the electron going through the slits, where it turned into that probability distribution, in some sense it is in all those places at once and in none of them at all. I don't know until I make a measurement of it. It's in a superposition of all of those states. And the cat is a good example because there's only two states. It's either dead or alive in an equal superposition. Then when I open it up and measure it, I collapse the wave function and I find out, well, it's not just that I find out. So it's not just that I don't know at this point. The universe doesn't know if the cat is dead or alive. It hasn't made up its mind. Okay? When I make the measurement, the universe makes up its mind, and the cat is either alive or the cat is dead. Now, that might sound spooky because it seems like, how does the universe know I'm looking at it? But again, I want to point out this is an analogy. A cat is not something you can actually put in a quantum superposition because it's so big. Remember, like I showed with me going through the door, I don't exhibit quantum-like behavior on my length scale. But if you did this with a single subatomic particle, you could put it in a superposition. And as for how does it know when I'm looking at it, well, how do we make a measurement of something? Whenever you make a measurement of something, if you're just looking at it, you bounce light off it, the light bounces back into your eye. So it's not a sort of, we shouldn't put an anthropic spin on this. It's not about a conscious being looking at something and seeing, I see the cat or I see this particle. It's about the physical process of a light ray scattering off of the electron or whatever it is and scattering off. That scattering process determines the state, or it makes the state determined, rather.
I find that more plausible to believe than putting a cat up. So could that be superseded by that?
Yeah, well, yeah.
The cat itself is either, there may be a 50% probability as to whether it's alive or dead, but it is actually alive or dead.
No. It's sorry, go on.
The cat knows if it's alive or dead.
Well, that's a very good point. That's a very good point. And it's one of the flaws in this analogy because the cat can observe itself. So in some sense, the cat never gets into a superposition because it's making an observation. Oh, hey, I'm alive. Oh, hey, I'm not alive.
It could think it was asleep, but it wouldn't be able to think it was.
The sleeping part might be too complicated for this model. Yeah, that's a great question, though. But the point is it's an analogy, so we're neglecting the fact that the cat can observe itself. We're only thinking about us observing it. But as for your question, surely it's one or the other, and it's not, it's just that we don't know it. You have to assume these superpositions, because if you assume that it is in a definitive state, when you do other calculations that rely on things being superpositions, you get the wrong answer. So the calculations that I'm referring to are more complicated than one single subatomic quantum superposition. It's when you have multiple ones interfering with each other. You have to treat them all as indeterminate. They sort of interfere like waves in this fuzzy probability cloud. And then when you make a measurement, that's when the wave function collapses, but not before. So you have to assume they are truly indeterminate when they're all interacting with each other, or you get the wrong answer. So it's a tough one. So again, it sort of comes back to, this is science that we've tested. It's a completely different way of thinking about the laws of nature, but it's something we can test. It's something we can build technologies on. But it doesn't make sense to anybody. That's the other point. We saw 2 Nobel Prize winners saying it doesn't make any sense. It ultimately doesn't make any sense. But it's calculations we can do. It's technology we can build. Yeah.
So it's the probability that happens then, because really, when you're talking about predicting
Yeah.
based on non-physical things,
Yeah.
the law of physics, the probabilities must be super accurate then.
Yeah.
What could be that potential probability? Is it just based on the observations that you're making at the time? Obviously, it's probable, and then you don't know the outcome until the actual outcome is
Yeah. Yeah.
But those probabilities must be very, very accurate to be able to base them on your predictions.
Well, so it's like, imagine you did like 1,000 of these experiments in one go. You can relate the outcomes of the experiments to the probabilities. So say, for example, in this case, you ran this experiment lots of times with lots of cats, and you found 50% of the cats were dead and 50% of the cats were alive. That would sort of match up with the prediction. You do a similar thing with the electron passing through the slit, forming this probability distribution. You measure where is the electron 1,000 times when you do the experiment, and you find the middle part where we had the larger probability, the proportion of electrons that are found there precisely matches the probability that the electron should be found there. So yeah, we're testing it against experiment versus the probability. Yeah, I think you had a question, didn't you? Yeah.
Yeah, it's, I just wanted to ask you yourself, between the Copenhagen and the multiverse, which one, because you put your hand up for one, and I couldn't remember which one it was.
I put my hand up for the many worlds, but to be honest, it depends how I wake up in the morning, which one I prefer. But today I feel like many worlds.
Which one you lean more
I like the many worlds because there are some interpretations of string theory that are neater in the many worlds interpretation, and I'm a long-distance fan of string theory. I'm not a string theorist, but I appreciate it. So I like that a little bit more for that reason. I think you had a question, yeah.
How do we know it's a 50% chance? Because random, and the particle doesn't decay, it could decay, but it's still alive. But if it decays, it can't be alive on the next time it has a chance.
So
So
it's not
there's
necessarily.
more of a chance for it to be dead.
Not necessarily. I mean, I think I've set this one up so it's 50-50, but you could have it so that it was not 50-50. You could do a similar example where it was 60-40, for example. So I've done the 50-50 because it's easy. Yeah, that's a good question, though. There's this idea, this completely out there idea of quantum immortality, which sort of goes back to what you were saying about, well, the cat knows if it's dead or alive, right? Well, imagine we are the cat and we're in the box. If you believe in the many worlds interpretation, it's very hard to imagine yourself existing in a branch of these parallel universes in which you would ever die, because at that point you would stop making an observation of the state of the universe you're in. So there are some bizarre theories that actually in the world we exist in, as in you exist in, you have to think you yourself first person, you will never die in this world, because you have to exist in a world in which you can observe your own existence by the many worlds interpretation. So for me personally, I can say I'm never going to die because I couldn't possibly exist in a world in which I would die. Now, in your world, I will at some point die, certainly, and in my world, you know, you will all die in my universe that I'm referring to here. But in mine, I will never die, and in yours, you will never die. It's some part of it. I don't know how I feel about that, but yeah, you had a question at the back.
I'm still wrapping my head around the many worlds, but would they all sort of run concurrently? Because I can't square it off energetically if there's multiple universes, but I just don't know it that well.
Yeah, they're totally separate. So there is still only one universe. There is only one me and one laws of nature and one set of processes going on in my universe. But it's part of some larger probability space. It's not a physical thing where you could go from one to the other. To be honest, there isn't really a way we can think about it in a bigger picture of these things occurring in one single space, in one single multiverse. It's more of an analogy, in a sense, for understanding the probabilities. Yeah, that's a tough one. Yeah?
When you calculated the wave function for yourself,
Yeah.
you got 4 times 10 to the minus 36.
Yeah.
How does that compare to the size of an atom?
So size of an atom is 10 to the minus 10, so 0.90 is 1. The nucleus of an atom is 10 to the minus 15, so 0.14 zeros. And the individual proton is about the same size.
So when you're testing, so if you're trying to observe the wave function for yourself, it's
Yeah.
always going to be inside the atom.
It's smaller than the Planck length. It's smaller than the smallest possible length in the universe.
But when you're doing the wave function for photons, they're bigger.
They are larger. And even electrons, even matter particles, they have wavelengths that are comparable to things we can observe. So if you fire an electron beam at a sheet of graphite, the spacing between the graphite atoms is very close to the wavelength of the electrons, and so they spread out and form a wave-like interference pattern. This is one of the experiments we use to prove that matter particles also show wave-like properties. Okay? Yeah. All right, I think we'll move on now, just because I've got some more stuff to talk about. You go forwards again, Ashley. Okay, so particle physics. I want to talk about the goals of particle physics. What do particle physicists want to do? So this is the most reductionist of all the sciences. We have two goals. We want to describe all matter in terms of its smallest component parts, fundamental particles, as I will describe them as being. And we want to describe all forces of nature, all the interactions between these fundamental pieces of matter, in terms of a small set of fundamental forces. So there are lots of use of the word fundamental, as you can see. So here I have an atom, the atomic nucleus, electrons spiraling around the outside. Next slide, please, Ashley. Now, if I zoom in on the nucleus, there are different particles inside. There are two specifically, protons and neutrons. So I zoom in on the nucleus, I see the proton. Next slide, please. I zoom in on the proton. I see it itself is made of smaller parts. It has 3 smaller pieces inside it, 2 quarks that are called an up quark. Up is just the name, and one that is called a down quark. Okay, these are 3 different little pieces. And next slide, please. Now, if I zoom in on a quark, I just find more quark. I don't find anything, any smaller components within the quark. This is what I mean by fundamental. It's not something I can zoom in on any further to describe what's the machinery inside. It is the smallest nugget of matter you can possibly have, okay? And there are lots of these smallest nuggets of matter. Next slide, please. And again, please. Well, I'll come to what I was going to say in a minute. Okay, yeah, moving on, sorry. If we combine special relativity and quantum mechanics, so these are, again, two of the most successful theories of the early 20th century. When we combine these two together, they give us something called quantum field theory. So special relativity is Einstein's 1905 theory of space and time and light, which we're going to talk more about next week. Quantum mechanics, we've just discussed. So 1926, in order to build up a more coherent picture of how light really behaves, given that light travels at the speed of light, so that's all stuff Einstein's talking about in 1905, but also given that light is a quanta, you know, we've talked about these photons, these quanta of light, we have to combine these two ideas, quantum mechanics and special relativity, and they form quantum field theory. Next slide, please. So quantum field theory, to put this in a nutshell, describes matter particles at the most fundamental level as sort of excitations of some underlying field. Now, a field is basically a region everywhere within a region of space. A field takes a particular value. So you could talk, for example, about the temperature field within this room. You know, if you're stood by the door, the temperature's a little bit lower. Maybe it's more like 19 Celsius. If you're stood up by the lights, maybe it's more like 23. Every point in space has a temperature value assigned to it. So this is an example of what you would call a scalar field, because the value assigned at each point in space is just a single number. Now, a quantum field fluctuates according to the laws of quantum mechanics, meaning there's an uncertainty on what the field is doing at a given point in space, just like the uncertainty we saw for whether the cat is alive or dead, whether the electron is here or there. And the particles, these pieces of matter as we understand them, are fluctuations where the field has a little peak, a particle appears, perhaps it stays there, but perhaps the particle disappears as well. So what this diagram, what this GIF here is showing is the sort of fizz of fundamental particles popping in and out of existence and then, you know, dissolving back into the vacuum, appearing for a short period of time and then disappearing. This is happening everywhere all the time. Okay? Next slide, please. So what is matter? Is it a particle or is it a field? Next slide, please. It's both. Next slide. Sort of. So let's take an example. The scattering of electrons. So if we sort of fire two electrons in towards each other, you have an initial state, which is two incoming electrons moving towards one another. Something fuzzy happens in the middle, a la sort of quantum mechanics. And then we have electrons coming out at the end. Okay? So something in the middle, indeterminate, is happening, just like we saw with what's going on with the electron until we measure it. These are things we can measure. We can measure the electrons coming in. We can measure the electrons coming out. These arrows here represent the motion of the electrons towards one another. The time axis going up means this is earlier in time, and the higher up in the diagram you look is later in time. Okay? So this force is controlled by the electromagnetic force. This repulsion, is controlled by the electromagnetic force. Because the electrons are both negatively charged particles, when you get them close to one another, they will want to push apart. In the same way as if you put the north poles of two magnets together, they will push apart. Okay? Next slide, please. So in particle physics, we describe forces as due to the exchange of a force-carrying particle. So for electromagnetic repulsion, this force-carrying particle is the photon. So this is one diagram showing how these two electrons might repel one another. Okay? The rules of this particular kind of quantum field theory of how electrons and photons interact was thrashed out in the 1920s. Next slide, please. So is this it? I mean, is this what's going on when the two electrons repel? Are they just throwing a photon at each other? The photon tells them, by the way, you're both negative, you should be repelling, and that's it. What happened to the fuzzy indeterminate cloud? Next slide, please. No, the fuzzy cloud is still there, okay? We can't get rid of quantum mechanics quite that easily. Next slide, please. So it turns out, though, that this fuzzy indeterminate cloud contains all of these different ways for the electrons to exchange photons and tell each other, by the way, we should be repelling, okay? In the same way, you have a sort of quantum superposition of dead and alive, electron here, electron there. The fuzzy indeterminate cloud is a superposition of all of these different ways the electrons can interact with one another to lead to a repulsion. And you have to include all of these, okay? Each of these little pieces, these diagrammatic representations that are called Feynman diagrams, represents a piece of the probability that the electrons will bounce off each other in the way shown, okay? But it's still indeterminate what's going on in here. There's all these different ways. Maybe they swap one photon, maybe they swap two with one bouncing up here, maybe they spontaneously turn into an electron and an anti-electron, fuse back together and then push away. There's all of these different possibilities, and each one of them is important to calculating the probability. However, fortunately, all of the ones after the first one become increasingly smaller to the overall contribution. So it's like, say there's a 50% chance, this one is 0.5, 50%. Maybe this part here is 0.001, so that tells you it's 0.501. And all of the other pieces are worth less and less and less. So even just looking at the first one, you can tell roughly what the probability is. It's only if you want much higher resolution, you look at the later terms. Okay, next slide, please. Okay, so the particle zoo. So in the 1950s, particle physicists were discovering tens and tens of particles every single year. So much so that Willis Lamb, in his 1955 Nobel acceptance speech, said physicists should be fined for discovering new particles because there were so many. Like I said earlier, physics was starting to look more like botany. We were just collecting lots and lots and lots of particles. We didn't know how they fit together. Are they all part of some broader picture? Are they fundamental or are they composite? So fundamental, again, means you can't zoom in on it anymore. It just is what it is. Composite is like the proton. It's made of smaller pieces. Okay? Next slide, please. So Murray-Gell-Mann figures out that all of these particles that we've discovered are really just combinations of only 6 up here. I think I wrote 8 there. I don't know why I wrote 8. I got confused because he calls this the eightfold way in a sort of analogy to I think this is a tenet of Buddhism, actually. He thought it was quite funny to call it that. I don't know. But he figures out that all of these particles we discover are combinations of only 6, these 6 varieties of quarks, which he predicted, and then over time we discovered. So he predicted the existence of these 6 particles, and over the following decades we discovered that they do indeed exist, and they have all the properties he predicted they should have. Again, that's coming from the sort of mathematical framework behind particle physics. It's not just we're guessing. Maybe there's another quark, maybe there's another one here, another one there. It's doing the equations, doing the maths, and then measuring and discovering these particles for real. Okay? Next slide, please. Okay, so this introduces the standard model of particle physics, which is our best theory of what stuff there is in the universe and how do these pieces of matter interact with one another. So in the red box here, we have all of the visible matter. That is the quarks and the leptons. So quarks combine to make protons and make neutrons. Leptons, one example of a lepton is the electron, but there are others as well. And then in the blue box, we have the force-carrying particles. So this describes nearly all of the forces in nature. The one that's missing is gravity. And the matter particles, they describe all of the visible matter in the universe. Next slide, please. So you can see there's some caveats I've put here. Despite me calling this the most successful theory in physics, again, tested in many ways to 1 part in a trillion, there are these gaps I've left. So all the visible matter, first of all, that looks suspicious. And nearly all the forces, well, the nearly we know corresponds to gravity not being covered in this model. But what about the visible? Next slide, please. So visible matter is all the stuff we can see, all the stuff that the Earth is made of, the stars are made of, all the glowing stuff you can see in this galaxy is visible matter. But that only corresponds to about 5% of all of the matter, all of the stuff in the universe. 95% of the matter in the universe is completely mysterious to us. We call it dark matter, which is a bad name because it's actually completely transparent. It doesn't emit light. It doesn't absorb light, so you can shine a torch right through it. You can move your hand right through it, because the reason my hands don't pass through one another is that the electrons in my hand and the electrons in my other hand push against one another because of the electromagnetic force. Dark matter doesn't feel the electromagnetic force. It only feels gravity. We know for sure it feels gravity because it has a weight. It might feel another force we call the weak nuclear force, but even that is not certain. But we know it's there, despite not being able to see it, not being able to touch it, despite having never found it in any of our particle detectors. We know it's there by looking at the rotation of the galaxies. So this top curve on the right here is a galaxy rotation curve. So what this is showing is how the speed of rotation of the stars as you go further out away from the center of the galaxy, how this changes with distance. So what you see here is curve B, the solid one at the top, is what we actually observe when you look at the speeds of different stars in the galaxy. The further out away you go from the middle of the galaxy, it changes a little bit, but actually it's quite flat. It's pretty flat, okay, this solid curve. Now, if you do a prediction, so again, we're trying to match observation with our theory. If you do a prediction based on how much matter it looks like there is in the galaxy, by counting the stars, making assumptions about how close together they are, etc., you get a completely different curve from what we observe. So our theory completely fails. Now, if instead you count all the stars, you include all the visible matter, but you add in some extra matter that you can't see, that's completely invisible, and again, you might be thinking, this is just physicists making stuff up as we go. But if you include this, the predicted curve perfectly matches the observed curve.
How do they know that there's just not more matter than they were trying to calculate in the galaxy?
Because we'd see it. If it's visible matter, we'd see it. Yeah, we'd see it. So when we include this invisible matter, this dark matter, it perfectly matches the observation. Okay? Next slide, please. But what is dark matter? Ultimately, we don't know. Remember, not the periodic table. The standard model shows all of the fundamental matter particles. Dark matter is none of these. We don't know how dark matter fits in to this picture, if indeed it does. There are lots of crazy theories about what dark matter might be, a lot of them involving extra dimensions. These are the ones I typically work on. Some involving primordial black holes, WIMPs, which stands for weakly interacting massive particles. Lots of crazy theories. But ultimately, we don't know what dark matter is. Next slide, please. So you might be tempted to say, well, why is it anything? What is the evidence for it? Perhaps we just don't understand how the galaxy spins well enough. Well, one of the other most convincing pieces of evidence for the existence of dark matter comes out of the bullet cluster. So this is a small cluster, and the colorations here are showing densities of matter. So what's happened here is two clusters have collided, two small globular clusters. They've passed through one another. Now, the redder parts are the visible matter, the bits of matter that will hit one another if they collide. they have not passed through as far as this stuff highlighted in purple, which is not really glowing purple, but you've colorized it so you can see it. And this is matter that has pushed a lot further out because it doesn't interact, it doesn't collide with other pieces of matter. So this is what we call dark matter. This is a direct observation of dark matter. We're also trying to find dark matter in particle physics experiments, so using colliders, looking at one of the things I'm working on is how we might be able to detect dark matter by looking at supernova neutrinos from the sort of cumulative history of supernova in the universe. But ultimately, I guess what I want to convey here is that dark matter is very much a work in progress. We don't know what it's made of. We know it's there. We have lots of evidence that most of the matter in the universe is completely invisible, but we've got no idea what it's made of in reality. Next slide, please. So next slide again. We might have some time for questions at the very end. But I just wanted to plug, if you want to talk more about special relativity next week, I'll be doing that at the same time, same place. Next slide again. And if you want to see the lecture slides I've used for this talk, these are all uploaded on my website. You can see there. And, oh, my laptop's going to die. And we've run out of time. That's good timing. So thank you very much.